Right, I think I'm back, but I'm still dropping a lot of frames, aren't I? That's gonna be a bit of a challenge, but either way, I'm just gonna keep streaming, and let's just get on with the board. While we're doing that, and we're still waiting for the student to get in. Oops, wrong one. Should be that. Let's translation it. Oops, forgot my calculator. Let's put that up here. There we go. All right. Right, so while we were waiting, she did say we're gonna do about 2 minutes. I think she's also having some trouble with the site right now. So while we are waiting, 4 minutes. There we go. Let's take a look at the problem. So that we need to do. Still have a few problems we need to do from before. This one's done. I'll just look at them first. Okay. This one's done. Not yet. This one's done. Okay. We have some new problems here. Again, I see a lot of problems against relativity. But yep.
Hello.
All right. Hi, Geeta. Good afternoon. Okay. All right. So, how's everything today? How are you feeling now?
Much better, thank you.
Right. So, okay.
How about you?
That's weird. I didn't get the notification that you joined until that.
Huh,
Weird. All right.
that's strange.
Okay. And everything's a bit weird. Even the stream's lagging a whole bunch right now. All right. Either way, let's just
Hmm.
get it on. All right. So, let's see now. Which am I gonna share with you? There we go. All right. So let's go to the first problem. We're gonna do a problem from last time. This image. But I'll share this board with you later. This is a new board because we ran out of space on the other one, right?
Okay,
All
thank
right.
you.
Okay. So I might as well share that now while we're waiting. Okay, so here's the first problem here. We have a hypothetical planet with a radius twice of that of Earth, orbiting the Sun at the distance twice that of Earth from the Sun. Okay, so determine the average intensity of solar radiation on this hypothetical planet in terms of the solar constant on Earth S. Okay, so this one's actually pretty easy. Intensity is proportional to well, let's not even do that. That's gonna be power over area, right? Let's start with that. So here's the thing: the power output is from the sun, so therefore P is constant. P from sun is constant. Okay, is constant. So that's so what do we do here? That means the intensity is proportional to the area, and the area here, what's gonna be the area here if this were the sun and this is the planet? Okay, okay, I'm gonna make it a bit more exaggerated so it's a bit easier to see. Okay, if this were the sun and I'm gonna make the planet this size. Okay, now that planet is going to be a distance, in this case it says twice that of Earth, right? So let's just say that's R for now. Okay, and also that the radius of the planet is also, we need to consider that here. So the area that this covers, more or less, okay, so in these cases the area is gonna be half, actually no, just 1/4, 1/4 of the area of the sphere, um made by the planet. Okay, okay, planet. So this is in terms of R, right? Now another way of thinking about this is I'm going to hold on, I'll remove this first. Oops. Okay. It's gonna be easier to see this instead of looking at this in terms of the radius of the planet first. We're gonna look at this in terms of the sphere around the Earth. So this is the Sun. Okay, this is the sphere around Sun. Okay, the area of that sphere. Okay, the area of that sphere, that's gonna be 4 pi r squared. Right? That's the area of that sphere, and then we're gonna put this in here. Okay, and we're gonna look at this as the shortcut here, and the shortcut here would be this planet is a disk on that sphere. Shortcut. Shortcut. The planet is a disk on the sphere. Okay. So what's that area of that disk on the sphere? It's going to be, in this case, that's gonna be pi r squared. Okay. So the area of the planet is gonna be pi r squared in this case. One last thing here is that the intensity here depends on r. Okay. I think I'll change color on that one. So again, the intensity is proportional to big R, the distance from the sun. Okay, but the actual amount of power that, in this case, I'll just put it here, the power received by the planet is proportional to, well, r squared, should be r squared here. The power received by the planet is proportional to small r squared. Okay. All right. So going back here now, so that's the whole idea. Let's kind of look at the whole thing again. So if the Earth gets the solar constant S, the intensity S is on the Earth. Let's just write it here. The S over the intensity. This should be equal to, the easiest way to do this is the intensity on the Earth is S, and that's going to be, let's use this same thing here. The power output on the sun. So in other words, we want this bit. We don't really need the amount of energy here. We just need the intensity. So in this case, we're gonna use the one related to R. Okay, so this is gonna be pi 4 pi r squared divided by 4 pi. For the other planet, it's gonna be twice the distance. So that's gonna be 2r squared. So what happens? 4 pi cancels out. So S over I will be equal to, the r squared also here cancels out, right? We're left with 4. 1 over 4. Okay. Hold on. Did I do that right? Hold on. I forgot something. Proportional to 1 over r. Oh, sorry, my mistake on that. Okay, so we're gonna do 1 over here and a 1 over there. So we're left with 4. Okay. So that's gonna be 4 over 1. In other words, the intensity on that planet is equal to 1/4 of S. Okay. So the answer is C. So again, intensity, if we're just talking intensity, we would just want the distance from the sun. Okay. If we're talking about the actual power that's landing on the planet, we consider the radius of the planet.
Okay, and the intensity number that we have, the 1360.
Mm-hmm. Yeah, that's gonna be the value of S, correct?
Huh. And is it including the, like, is it the full power that arrives, or is it only the like 1/4 that we receive?
Okay. If we're talking about the Earth or the hypothetical planet.
The Earth.
The Earth. The Earth, we will get the intensity equal to S. Okay? The total energy we get, though, is we multiply that by the area of, yeah. We multiply that intensity times area equals power. Yeah. So the power that the Earth takes in would be equal to that, the equivalent area that lands on the Earth. The shortcut again is you don't consider the Earth as a sphere here, you consider it as a disk. Okay. It's a rather long
Okay.
explanation why we have to do that. So just assume for now that the Earth is a disk as it absorbs radiation. However, when it emits radiation, you go back to a sphere. Okay.
Mm-hmm.
All right.
Okay.
All right. If we have time, I'll explain why that happens later. Okay.
Mm-hmm.
All right. Next problem here is still about solar radiation. It's the one. I think have we done this problem yet? I think we have. It's the one where it's the one with the image of the energy from the sun is going down and two arrows are going up, symbolizing this. Here, we've done this, right?
Um.
I think so, but I'm not so sure.
Uh.
Let's just go
I
over it, I
don't remember.
guess. Let's just go over. Let's go over it now. So, oops, why clone? Okay, let's lock that. Okay, so first of all, what does it say here? The power of the radiation absorbed by the Earth's planet is P, and it's given here. This is a given equation. Okay, so show that the average intensity of the radiation that is absorbed by the planet is given by this. Okay, um, that's pretty easy actually because in this case, remember that the Earth, hold on, across the Earth's surface, average. Okay, so we're averaging it over the Earth's surface now, right? Okay, and it's average. So, we know that power over area would be equal to the intensity, and therefore that's gonna be, you're given that equation, 1 minus alpha times S pi r squared, right? Now we're gonna divide this by the area as well, just like that for now. Okay, because that's the numerator is just the power. However, the area of the Earth will be pi r squared. There should be a 4 here. 4 pi r squared. Then the numerator is still 1 minus alpha times s pi r squared. So what happens? The pi cancels out. R squared cancels out. We're left with 1 minus alpha s all over 4. And that's the solution here. Okay. Right there. Okay. The reason again why we're doing 4 pi r squared for the area of the Earth here is because we're looking at the average throughout the whole surface. Okay. All right. So here in part 2, this one's pretty straightforward. You're given the albedo, right? 0.3. S is a constant. It's in the data booklet. Um, are you given the radius of the Earth here? No, we don't need it because of that shortcut, right? So all we have to do is apply the formula here, the 1 minus alpha s divided by 4. Okay, so that's gonna be 0.7, 1 minus 0.3. The s is in the data booklet, so I'll just keep that as s for now. And then divided by 4. So that's gonna be 0.7 s over 4. Calculate that with the value from the data booklet and you'll get the answer. Okay, that's why it's only 1 mark. Okay.
Okay.
Okay, again, 3 marks for radiation absorption and emission of radiation. This time though it's in terms of molecular energy levels. Okay, so this is not gonna be simple in terms of just energy. um just energy exchange, we're gonna have to involve quantum mechanics a little bit here. Okay, so what are the 3 marks? Again, without looking at the marking scheme, this is what I would say. I'm gonna include a 4th mark just to keep it safe. Okay, so the first mark is that the infrared radiation radiation incident on Earth, okay, does not match. So let's add the word here. Infrared radiation energy. I would energy incident on Earth. I'll put that in bracket. Does not match energy level differences in energy levels in what? In the molecule of the greenhouse gas. Okay, so that's the first mark. I think I'm gonna if I'm gonna be generous, this is gonna be 2 marks at the moment. Okay, but okay, so let's remove that and let's remove this. Oops. Okay, that here. Now the second mark I will put here would be so the Earth. This is gonna be the second mark. I think this is gonna be third. Okay. The Earth that. Okay, from the sun. Let's put infrared here. Radiation from the sun. Okay, and the third mark here is the Earth re-radiates that energy. So Earth re-radiates the energy as infrared radiation whose photons have energy equal to molecular energy level differences. Okay, and then the fourth one is now involving what it does. So the greenhouse gas will absorb and re-radiate the IR from Earth. Okay, to the planet. That's it. So these are the safe 4 marks that I would write. In fact, there's only 3 that you need. Okay.
Okay.
All right. Okay, any questions here?
No, it's okay.
Okay. We've done the pendulum problem, right? The one with the bucket and the pin.
Yeah.
Yeah, so we'll skip that. Okay, let's see. Which one is not relativity at the moment?
Mhm.
The distance between... Oh, okay. Let's do this problem here. This one is the Doppler effect. It's the one with the sensor and the spring and the speaker. Yeah.
Mhm.
Okay.
I think there's 2
Yeah.
screenshots for that one.
Yep. I'm copying the other one right now. Okay. So for the first one, we don't need to do the first problem. I think you got that right.
Yeah.
Okay. So let's go put this. Put this here. So the distance between 2 consecutive points where the intensity of sound is a maximum is 14 centimeters. So you have to determine the speed of the sound. You're supposed to get an answer that's close to 340 based on that clue from the second part, right? Okay.
Yep.
All right. So let's take a look at the problem again. So what's happening here? The sensor is here. It doesn't really move, right? Does the sensor itself oscillate according to the problem? No,
No.
right? But the sound is reflected off the floor. So this is important. Since the sound is reflected off the floor, we have a standing wave. And standing waves make it a bit easier to analyze because we know that there will be nodes and antinodes, right? Okay, now what is given here? You're given that the frequency, I'll put this here first, the frequency is 1200 hertz. So that means we can somehow determine the wavelength later on. Okay, so now let's take a look at what B says. See if it gives us a clue. It says here the distance between two consecutive points where the intensity of a sound is a maximum of 14 centimeters. So in this case, okay, in this case, the spring is not moving yet, right? This time it's the sensor that's being up and down. So in other words, let's say that you have a maximum here, right? And then you have another maximum here. And we know that from here to here is 14 cm. And we know now, we know that this is a standing wave. So this must be an antinode. And I'm going to draw the let's zoom in a little bit. Since that's going to be a maximum sound, we're going to put a part of the antinode here. The other part of the antinode would be on the other side because we know for standing waves that it's every alternating. So basically the distance between that and that. Okay, so if you continue this, if you go back to another 14 cm here, like so, we're gonna get another antinode here. So we're gonna get that, right? So in other words, this is half a wavelength because it's maximum to maximum. So we know from here that 1/2 of the wavelength is equal to 14 cm. So therefore, the actual wavelength is 28 cm, right? What's the actual question?
Oh, right.
Okay, so what's the actual question here in B? We're determining the speed of sound, and that's easy now because we now have a maximum. We now have a wavelength, and we now have a frequency. So what do we do here? Frequency times wavelength equals the speed of sound. I'll just write sound here, right? And that's gonna be equal to 1200 times 0.28. We have to convert this to meters. 0.28 meters. Okay, so that's hertz, that's meters, and that's gonna give us, I don't know what that is in my head, calculate. 0.28 times 1200 is gonna give us 336 meters per second. Okay, here. Okay.
Yeah.
All right. So calculate the range of frequencies recorded by the sensor given that the speed of sound is 340 meters per second. Okay, this one is there some information that we need to go through? Because by itself and with the information given earlier, I don't think we can answer the second problem. There, unless I missed some information.
One moment.
Go ahead, please. If you
I'm
can
looking
find
at it.
yeah. If it starts to oscillate, I think that's the situation here. Because right now, from for A
There
and B.
was.
Go ahead, go ahead.
Mhm.
Go ahead.
So it said, yeah, it is below the oscillating speaker.
Mm-hmm.
The sensor is now positioned directly below the oscillating speaker,
Mm-hmm.
and then it says the oscillation of the speaker are very lightly damped. The support S.
Okay.
Um,
Oscillation is lightly damped, right? Okay. Is there any? Sorry.
oh wait, sorry. So
All
I
right.
should have just sent a screenshot.
Yeah,
I'll
sure,
send
sure,
it.
sure, sure. I think, okay, let me get that screenshot here. Hmm. Still not here. Let's wait a bit. All right. So anyway, yeah, that's the information that we need. I think it's the oscillation is what's gonna change the frequency. Okay. But
Yeah.
okay, here's the deal though. While we're waiting for this to come up, I'm gonna say that this is gonna be about the Doppler effect now. Okay, because that's the situation we're in. We have a change of frequencies. Doppler effect. We're in. We have a change of frequencies. Doppler effect. Okay. Now, in other words, we need to kind of determine the maximum and minimum speeds of the oscillation. So that's what we'll start with. Even if we don't, oh, there it is. Finally came in. Okay. So the idea here now is in the oscillation, there's going to be a maximum. There's gonna be a maximum frequency and there's gonna be a minimum frequency. Okay. The maximum frequency will occur. Okay. When the okay, in this case, if this were the sensor, and then this is the weight, okay, when the weight is moving down at this fastest, okay, that's going to be maximum frequency. Okay, now if it's moving upwards at its fastest, it's gonna be where we have the minimum frequency. Okay, all right, there we go. Hold on, let me just copy that now. Okay, this is useful because it's telling us what the displacement is, what the amplitude is, and we're given the spring constant and we're given the mass. So we can actually calculate um, the sure the frequency of the oscillations is about 60 hertz. That part I think you've solved. That's why you didn't send it over, right?
Yeah.
Okay. Now, the frequency of oscillations is already given to be 60 hertz. So we'll assume that you already solved part one. We are not gonna do that, but we will use that information to do this part. Okay, the calculation of the range of frequencies. The important thing here is we're given the frequency of oscillation. So what's gonna be the angular speed? The angular speed will just be 2 pi times 60 hertz, right? And that's gonna be 120 pi hertz. I'm gonna keep it as pi for now just to make it easier to remember and less, you know, less bothersome to work with. Okay, we'll get the final answer once we're actually done with the solutions. So that's the first thing. That's our omega. Uh, and the thing is, we have an equation to get the speed. We know the kinetic energy of an oscillator, right? What's the kinetic energy of an harmonic oscillator? Let's put max in this case. That's just gonna be I forgot again. I still can't remember that. Let's use the data booklet, or maybe you have it right now. Can you tell me the energy for a
Uh,
oscillating
no,
particle?
sir. I don't have it.
Oh, okay, you don't have the data booklet. All right, let me just pull it up real quick. But it has something to do with 1 half k um, x0 squared. Okay, I'm gonna make sure that that's correct, but I think it is. Okay. So in this case, hold on. So is there anything else we need? Oh, actually, we don't even need the frequency of oscillation just yet, right? We actually just need um, that's going to be also equal to 1 half mv squared. Okay, so because we're trying to look for the speed. So we okay, I just have the data booklet open here, just double checking that, just to be sure. Simple. Okay. Right. 1/2. Okay, let's use the other one then. Um, let's use this. I think it's easier. Actually, no, we just... Okay, we'll change the word, the K. Actually, no, that's still correct. Okay, we'll put K in there. Now, why is this the case? Because when you store energy in the spring, and we assume that it's 100% efficient, then all the energy, this is basically the energy of the spring. The energy stored in the spring. Okay? But all of that energy gets transferred to kinetic energy. That's why we can make this particular equation here. Okay? And of course, kinetic energy is 1/2 mv squared here. So since we have that, we're going to use this to find v squared. So what cancels out? The 1/2 cancels out. And then from here, v will be equal to x0 times the square root of k over m. Okay. It's not, is it given in the data booklet? Just making sure. It's not exactly given in the data booklet. We have to get this particular. Oh, actually, it is. It is. It's given in C1. Okay. Or is it? Oh, no. Centimeters or 0.15 meters. The mass is 500 kilogram, 0.5 kilograms, and then the spring constant is here given 8 times 10 to the 4. Okay. So what's K over M? So let's just put that in the calculator straight away. K over M would be 8 exponent 4 divided by the mass of 0.5. Okay, we take the square root of that. That's 400. And we multiply that by 0.15 meters. Okay, so the velocity is gonna give us 60 meters per second. Okay. Okay, so that's the maximum velocity. Let's put that in here. Now that we have the maximum velocity, we will now use that in the Doppler effect equation to determine the two possible frequencies. In this case, we're just gonna use, which one is moving in this case? Source or observer? It should be the source, right? Hold on. Fix
I
that.
think so.
Yeah, it's the source that's moving in this case. So moving source, we have we'll just copy the formula. It's this. Okay, so this is the formula in the booklet. That's the observed frequency equals the original frequency times the fraction v over v plus us. Still taking time. There we go. So that's a formula. All you have to do now is put the use the two possible values, plus or minus. V here again is the speed of the wave. So in this case, it's speed of sound. So in this case, F is equal to what was the question again here? Let's just look again. Range of frequencies, right? What's the frequency earlier emitted by the sensor? It's 1200 hertz, right? Okay. So that's going to be F prime is equal to 1200 hertz times the velocity, the speed. It's going to be speed of sound in this case. Use the one given at 340. And then we have 340 plus or minus 60. So we do both values to find the final answer. Okay. That's hertz. Okay. So in this case, what's gonna be let's put the calculator here. What's 340 divided by 340 plus 60 is 400. Okay. Times 0.12. Sorry, 1200. That's gonna give us one possible value. F1 prime is equal to 1020 hertz, and F2 prime will be equal to, well, we do the minus, so 340 divided by 340 minus 60, that's 280. Okay, so 340 divided by 280, and multiply that by 1200. That's gonna give us an answer of um 1457 hertz. So these are our two values. Okay.
And what do they mean?
This means that okay, let me go to main camera so I can show you real quick. Where's the main camera? Okay. So basically, um sensors here, speakers here, right? So when the speaker is oscillating, this is happening. And it's gonna be fastest here at this position, not here at the top and not here at the bottom, because at those positions the speaker isn't moving, the velocity is 0, right? So it's gonna be somewhere here in the middle. And here exactly at this position, two things could happen. It could either be moving down, or it could be moving up. So either up or down, right? So when it moves down, it's moving towards the source, and therefore the frequency is gonna be higher. The frequency observed is gonna be higher. Similarly, if you're here but you're moving up, then the frequency observed will be slightly lower.
Okay. Okay.
That's it. So that's a physical interpretation of that. 3, to determine the scale of the axis on frame to frame S prime. Okay. I wanna try something here because I'm not 100% sure. I haven't tried it yet personally. Well, not recently, so I can't really remember. I wanna try it again. But I think we can actually get the Lorentz the Lorentz factor from that angle that we have from before. Okay. All right. So while I'm pasting that,
Okay.
So in this case, let's determine the scale on the axis of frame S prime, right? Okay. Um, let's kind of look back into the equations. I want to see if this works first. I'll try to do this quick. Okay. So what's the equation again that we know that for example, what's T prime equal to? It's gonna be T dilated, so T gamma. T over T gamma, right? So gamma is equal to 1 over root of 1 minus V squared over C squared. This is always okay, let me reason it out again. Always less than 1, therefore always bigger than 1. It's less than 1, so this is also less than 1. Still less than 1, 1 over becomes bigger. Okay, so this is correct, more or less, yeah? And then L prime would be equal to L over gamma. Okay?
Yeah.
Okay. So what happens? So let's not change that. Let's change that to x. X prime and x. Okay. Okay. Let me think first if this works, but otherwise we'll use the equations. Okay. Nah, it doesn't quite work. All right. So okay. I think okay, the thing I'm thinking doesn't quite work, so we'll just revisit this, I think. We'll revisit it tomorrow. We're having a class tomorrow, right?
Yeah, we
Yeah.
have a class every single day of the week. I don't know if it's a problem for you.
Okay, I gotta double check, but if normally no. Normally no. Okay.
Okay.
But I gotta double check as usual. Okay, I'll get back to this problem and number 3, right? All right. Let's
Yeah.
go now. The
They're
one the
from
go ahead, sorry.
sorry, they're from Tsokos. I can send you
Ah,
the link.
all right, no worries. I actually have the link as well. Let's just remove that for now.
Okay.
We'll get back to that later. Okay. Okay, so let's go now to this next bit. You have the rocket again moving past a space station of proper length, 1,200 meters. So that problem, okay?
Yeah.
Okay. Two lights L1 and L2. According to S, L turns on t seconds before L2. Okay, so according to R, the lights turn on at the same time. The rocket was above the okay, so let's kind of look at this now in terms. I think the easiest way to do this is space-time diagrams again, right? Okay, and your space-time diagram is in fact given here on the in the next part, right?
Yeah.
Okay, let's just put it up here. L1, L2. Where's L1 here? All right, there we go. Okay, we're determining V, and we're determining something else here. Okay, so on the space-time diagram, what's given to us? We know that L1 turns 2 seconds, oh no, t seconds before L2. So L1 occurs first, right? Okay. Who are
According
we?
to S.
Okay, that's according to S. So this is S. I will just note that this particular frame of reference is S, right? So according to S, it happens. What is T though? Because that may be something here. Not quite. T
Oh,
according.
T is the time that
Okay.
L1 turns on before.
Okay. So so L2 happens second according to S. So L should be okay, how far along is L according to this? According to according to R, let's start with R first. According to R, the light turns on at the same time, and the rocket was above the middle of S when L2 turned on. Okay. Okay, we will do this here. Okay, so according to the rocket here, okay, so that's our rocket. These happen at the same time. So if we draw some lines here for now, that's the x-axis, and that's where the integral. Okay, so this is what we'll do. Okay, the easiest way to do this is actually use the fact that it happens at the same time for the rocket. Okay, so being that, that means we're gonna follow the rocket's x-axis like so. So you're gonna draw a line that's parallel to it like so, right? Something like this. In the exam you're expected to use a ruler, but for now I will just keep doing that. And you will notice that it intersects. This is the point. This is the point here, L2, L1. More or less that point. Okay. Why is that L1? Because we know that they happen at the same time, and this. Hold on. Did I do that right? Actually, yes, okay, so this is what's happening here. So this is gonna be on this line is where L1 happens. Okay, now according to this though, that's not actually L1, because remember that when this happened, this is the location of the rocket. This is the distance from the rocket, so this is x prime from rocket to L2. Okay, to L2. So we're gonna do the same thing here. We're gonna keep going like so. We're gonna keep it going like so, with another distance here, x. Okay, so something like this. I may have drawn it a little bit incorrectly because I wasn't using a ruler, but that's the idea. This is still gonna be x prime here, and this is gonna be position L1. Okay. All right.
Sorry, I didn't understand why we extended it.
Okay, let me undo and redo everything. Okay. Okay, but this part so far clear, right? For this bit.
Yeah.
Okay. So again, the idea is it's given in the problem Let's go back to the problem. It's given in the problem that L2 turns on is marked with the dot. According to R, the two lights turn on at the same time, and that the rocket was above the middle of S prime when L2 is turned on. Okay, so when L2 is turned on, so basically according to R, okay, let's just do this in terms of R. Okay, let's redraw this in terms of R. This is our rocket, and basically the two lights are moving with a velocity v going this way, right? Right?
Yeah.
Okay. When the lights hit R, actually no, we should not draw the things here. We should draw the other way around, going out like that first. So when it's here, basically when it's here, this is what's happening. The rocket is exactly at the rocket is exactly in the middle, right? Middle of S. That's where the rocket is. So in this case, the rocket is now moving. Even though it's moving, it's right in the middle of S. So in other words, you can consider that since those two lights turned on and then it's at the middle of the rocket, that the distance that no, not the distance that the light travels, but the position of the light. Hold on, I think. Okay. Hold on. Okay. So let's erase everything here first, like so. So again, going back to L2. Okay. So when L2 turns on, according to R, L1 also turns on according to R, right? So
Yeah.
okay. So when does that happen? So okay, let's draw. Okay, since L2 is a beam of light, we can draw its world line here as well, right? And its world line doesn't change. It's always going to be like that. 45 degrees from the from either axis, right? So according to this is okay. I think we're getting too complicated here. Hold on. Draw a dot to indicate L1, determine V, and use T using a Lorentz transformation.
I think it was correct because
Yeah.
on the mark scheme it was at minus 600 and then they drew a parallel line.
Okay, so L2 happens at the same time when the light goes to that, right here. So the light curve goes here. So we need to determine. Hold on. Where is L1? L1 happens at the same time. So we need to draw there. We need to draw a light ray. Okay, I think I got it. I found a. Okay, this is easier. I can get the. No, I cannot. Okay, so where is 45 degrees though? It's gonna be a bit hard to draw. Okay. So L2 gets to the rocket at some time, and we need to draw the world line of the rocket. Sorry, not the rocket, the light. So that's gonna be the world line of. You know what? That's gonna make it easier. 500. This is 500, 500. So it's gonna be the world line's gonna be here to here. Okay. So when we don't do line, hold on. I pressed something. I cannot see it. Okay. Undo. Let's. Okay. So that's the world line according to L2, and therefore, when we do the time here, that's gonna be where the rocket sees L2, right? But remember that that the person or the rocket rather also sees the other line like so. So that's gonna be 0, 1, 2. So basically, we're gonna have to. It's like here in the middle. Okay, let's do the world line now from here to here of the other light. Okay, that other light will also have a similar trajectory, but going the other way. So something like this. Eh, why is that not working? There. So where would this be? Hmm. Okay. Okay. Three. Okay. There we go. So that's 5, 4, 300, 350. Okay. So that should be around here. Oops. Okay. Let's do that quickly. Should be somewhere here. Somewhat like that. Okay.
Okay.
Does that look right? No, it still doesn't look right. It should somewhere be in the middle. Okay, so somewhat like okay. I think I better draw a first line like that first. Make it easier to work with. Something like that, right? And we're gonna copy that line parallel to that. There we go. All right. Why did I do this the first line? Because remember, the speed of light would be the world line of light would be always between those two axes, no matter what you do. It's always gonna make that angle, right? So in this case, let's remove.
Okay.
Okay, let's remove that line for now. Let's make this other line a bit heavier. Uh, there. Okay. How do you make it heavier? Okay. Okay, there. Okay. So that more or less corresponds to what time was it sent over? When was L1 happening? L1 is according to S. Okay, let's just label it according to S. Okay.
Yeah.
All right. Let's get rid of that. Get rid of that. Um. So how do you determine V? How do you determine V? You basically just get Lorentz transformation here. You just use the Lorentz transformation for this point here. Okay. Actually, no, that's determining T during Lorentz transformation. You determine V by
Can we sometimes use the graph and find the gradient?
yeah, we do. We use the gradient. So yeah, so remember that the gradient, let's go back to that. The gradient is equal to V over C, right?
Of both
Ah,
of the lines?
let's do it like that. So the gradient of which one is it? The X prime. Is it the X prime? No, the CT prime graph. CT prime, okay? The gradient of that will be equal to okay, hold on. If this were 45 degrees, if the gradient is equal to 1, that should mean that the velocity equals c. So that means okay, and that's gonna be okay. So from here, that should be equal to x over tc, and that's gonna be v over c. Okay, yeah. All right. So the gradient of this would be equal to v over c of the CT prime graph, CT prime line. Okay.
Mhm.
All right. So
Okay.
yeah. So that's what you use to find v. Once you find the gradient, it's done.
And I can't use the gradient of the x prime.
You could, but it's going to be the reverse. Okay. That means
So
the
c over v.
gradient of x prime will be equal to c over v. Yes.
Okay.
Okay. Then from there, just use a Lorentz transformation to find what was that? To find the big T by what's T here again? The time seconds, right? Now, okay. According to this though, since it happened at this uh according to the rocket, we can use the Lorentz transformation to find the value of t. It is now. So once we find the speed, right? So once we find the speed here, you're gonna use that speed to change, to determine the time difference between the two lights turning on relative to s. Okay, and you have the equation in the, we have the equation there in the data booklet. Okay, I think we better go through this further
Okay.
tomorrow. So just we'll start with these, and then whatever other problems you send tomorrow. Okay. All right. So
Okay.
anything else you'd
Thank
like
you very
to
much.
ask today before we finish?
Not necessarily.
All
Not
right.
yet.
Not yet. All right. So in that case, I'll just see you again tomorrow. You have a good evening and continue resting. Okay. All right.
Okay.
All right. I'll see you.
Thank you.
I'll see you tomorrow. Bye
Have a
bye now.
nice evening.
You too. Have a nice day. Bye bye now.
Bye bye.
Yeah, that's the end of that stream there, and we'll just do that. Okay, just so we're clear, like I have said this before, and I am relearning relative. How long is a while? About 20 years. About 20 years since I actually touched relativity seriously like this. So I'm still kind of relearning it, but I do have the great the ideas on how to do it properly. I just really need to make sure that I'm doing it properly as well. Okay, so that usually means I take time to do that those problems just to make sure that we get the correct answer. Okay, so anyway, so that's the end of the stream here. So don't forget to like, share, and subscribe to the channel. Again, we're on YouTube, Facebook, TikTok, Instagram, and Twitch when we go live. So with that, I do hope you learned something if you're still here or you're watching later on. And with that, again, I will now have to say good day, good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everybody. Bye bye now.